Hey folks, I'm Auryn from Gnosisguild. I'm going to try to be good with mic discipline, but I'm god awful at it, so just gesticulate, tell me if you can't hear me. We at Gnosisguild, we've been working on a project called Enclave. It's essentially a protocol for encrypted execution environment. It's a protocol for coordinating the various actors that might be involved in an FHE computation. I think a succinct way to talk about it would be essentially an FHE coprocessor, but that hand waves over a lot of stuff. Today, what I want to do, and I guess I'm not sure how deep everyone is in FHE, but really wanted to just help give a few people a kind of light bulb moment with FHE in terms of what it can actually do and the fact that it is in a state that it's ready to start playing with, it's ready to start building things on top of. So I just put together a quick little example application, essentially simulating voting in a multi-party scenario. And so yeah, we'll just jump in. I think we're just going to step through the code. We've got plenty of time. No one's coming after this, so we can get as intimate as folks want. If folks want to just come up and we can literally whiteboard it or step through if you've got questions. If anything doesn't make sense, if I get anything wrong, then shout out, because this is all somewhat new to me as well, and so I'm learning as I go. And yeah, this is highly likely I've made mistakes. So anyway, yeah, we'll just jump in. I'm going to treat it like folks don't really know what FHE is, and so kind of treat this as a bit of a script, read through it, and yeah, we'll step through the code as we go. So this example demonstrates a simple, actually, is this big enough? Should I increase? Is that better for everyone? Yeah, and yeah, let's do it. Hold on just a second. Maybe the first thing we'll do is just run it so you can see what's actually happening here. So we're running a secret ballot here. We've got 1,000 votes being cast, 1,000 parties to the multi-party computation. And I think the big first part here that I just want people to understand is, like, this runs quickly. This runs on human scales. This runs on sub-human scales by a long way. And so in this case, tallying votes, it's super achievable to build programs that you can actually do and will be functional for real-world use cases. We'll hide that again and we'll go back into the code. So yeah, this example demonstrates a simple secret ballot system using the combination of fully homomorphic encryption and threshold cryptography, a multi-party computation. And so FHE allows us to perform operations over encrypted data, over ciphertext, while the threshold cryptography component allows us to distribute control over the secret key among multiple parties, such that the key can only be used when a sufficient number of them coordinate. In this example, we're just doing n of n because it radically reduces the complexity. So we'll simulate several parties coordinating to create a shared key, then simulate many voters encrypting their vote to that shared key, use FHE to sum the encrypted votes, producing an encrypted tally, and then that tally is decrypted using the threshold decryption scheme, where each party decrypts the tally to produce a decryption share, and the decryption shares are aggregated to produce a plain text output. So this implementation is a toy. It's not secure for a real election. Don't try to use it in production. In a real election, obviously, or a real kind of vote, the votes would be encrypted client-side, and only the ciphertext would be published. The decryption shares would be produced independently by each party, and only the plain text tally would be published. None of the kind of data that we have access to in the simulated environment. And yeah, again, demo code, probably broken. Don't use it in production. With all those caveats out the way, we can start kind of stepping through and check things out. So the first thing we're doing here is just defining the size of the kind of computation, so we can set up the parameters to the FHE scheme. So we're putting in the number of voters or the number of votes that will be cast. Here I have it set to 1,000. We can play around with this if we've got time at the end to define any, I don't know, to see how it scales. Then the number of, sorry, that's scrolling faster than I thought. The number of parties to the computation. So this is the number of parties that need to coordinate to decrypt the output. And with those two things, then we can play with the actual parameters for the encryption scheme. So the first one here is the degree. This is the length of the polynomial, usually n in the literature. It determines the size of the ciphertext. Larger degree increases the security, but also increases the computation and storage. Next variable here is our plaintext modulus. So the plaintext modulus determines the size of the plaintext space, quite literally how large the plaintext that you're wanting to represent can be. So plaintexts are typically represented as integers modulo this value. So a larger plaintext modulus allows us to use larger plaintexts. But similar to the degree, a larger plaintext modulus also increases the size of the ciphertext, so storage and computation, and it also increases the noise growth per operation. So in our case, each vote will be a single bit of information, a 0 or a 1, and we'll sum those votes to produce the tally. And so in our case, the upper bound of the plaintext size is equal to the number of votes cast. So a plaintext modulus, in this case, the largest potential option here is a little over 1 million, and so that's sufficient for a little over 1 million votes. Again, I have not, these parameters are probably insecure, probably don't provide us enough bits of entropy, so take it with a grain of salt or double check them. Then our last parameter here for the setup of the encryption scheme is the moduli. So moduli are used to control noise growth in the ciphertext in a leveled FHE scheme using a technique called modulus switching. Each modulus is a vector. It's a large prime, each modulus in the vector is a large prime number corresponding to the level in a computation. And computations are performed modulo the current level's modulus. So a larger modulus allows for more computation, but also increases the size of the ciphertext and the computation and storage costs. In this example, we're using a single modulus here, so it's not a leveled scheme. We're not making use of switching, and this is possible just because we're only doing addition. We're using the BFV encryption scheme, and so it has kind of linear noise growth with addition, but exponential noise growth with multiplication. And so because we're only doing addition, we don't need to have multiple moduli, or at least we have a lot of noise budget to play with. So yeah, our next step here is just setting up these parameters so that we can then go on to key generation. The last piece that we need for key generation here is this common reference polynomial. This is used by each of the party members to generate their public key shares. In this example, we're just grabbing some randomness seeded by the system, but in production, you probably want to use some publicly available source of randomness that all of the parties can agree on or the network can agree on, so that parties can't kind of manipulate this and potentially reduce the hardness of the setup. And so now we can, after kind of setting up all of our parameters, we can jump into actually generating keys and doing the FHE computation. So the next step here is each of the parties creating their keys. They generate a secret key. I'm going to navigate with my keyboard because it's smoother. So each of the parties generates their secret key and then takes the common reference polynomial, combines that with its with the secret key, does some other magic, and produces a public key share that is compatible with all of the other public key shares that were generated with this common reference polynomial. And this can happen in parallel, obviously, because there's no, well, I guess, unlike some other threshold schemes or unlike some other kind of multi-party computations, it's non-interactive. So we don't require we don't require the parties to the scheme to participate in a particular order or to kind of receive any additional data from one another in order to create their share. So it can be done in parallel and ultimately ends up being quite quick because of that. And then next step here is to aggregate these public keys. So the public keys are aggregated to create a single public key, or the public key shares, sorry, are aggregated to create a single public key that can be used to encrypt votes too. This is done simply by summing together all of the public key shares. And again, note because the public key shares are created using the same common reference polynomial, they are now compatible in a way that we can sum them together to produce a shared public key that requires all of the parties to coordinate in order to use. And then also note, because the shared public key is the sum of the public key shares, they can be aggregated in any order. There's no kind of interaction other than broadcasting your share to all of the other parties to the computation, and they can kind of add them as they arrive, and everyone will end up with the same result regardless of what order they sum them. Right, so next step here, we're going to create our plain text votes. So we're just simulating, in this example, every vote is either a 0. Yeah. I'll just scroll back up.
It's just on the key shares. I guess I'm trying to map back and forward between a setting where we might be using an NPC. So we could use a separate, so that public key is kind of like, that's our network key, our single network key, if you like. And then we just happen to be having the shareholders of that key also be the voters.
So these are actually separate. The voters don't create a key of their own. In this case, the voters are just encrypting data to that public key that was generated by the parties. In a voting system, we would have you would have some other registry, some other kind of gatekeeper for people to join the vote and essentially to prove that they're allowed to generate an input to this computation. But yeah, in this case, we're not generating keys for the voters.
So the parties aren't the voters?
No.
Sorry, okay.
Yeah, no, that's a good question, and thanks for clarifying. All right, so we've got our public key now, our shared public key between our party members, and we'll jump down and start simulating voting. So we are going to generate just randomly a bunch of zeros and ones, put them into a big array. This is fairly, is pretty straightforward. Next step is obviously to encrypt this. So each vote is now encrypted using that shared public key. Jump down here again, and let's see. Right, okay, so first step here, we were able to do this all in parallel. Obviously, this is, I guess, worth noting that, well, yeah, I just read the script that I wrote for myself rather than making it up as I go. So anyway, in a production environment, the votes would be encrypted independently. So this kind of computation is just distributed to the edge of the network rather than running kind of on one machine. And this is what kind of takes the bulk of the time in this simulation. And I guess another point to make there is just that in terms of scalability, what you see here is kind of slower than what it would be in production, because in production this is much more massively distributed. But yeah, essentially we're here taking our plain text, formatting it, or kind of converting it into a polynomial, encoding it as a polynomial, and then encrypting it to a ciphertext. I think the key thing to note here is for all of these plain texts are just either a 0 or a 1. They're 1 bit, but each voter adds in their own randomness, their own noise to the ciphertext. So even though that we're encrypting the same information to the same key, we end up with 1,000 distinct ciphertexts because they've all inserted their own noise. I think this is a really key piece to understand about FHE is how it kind of manages and how it deals with noise. And so, yeah, we now have our encrypted votes, and we're going to skip down to tallying the votes. So the votes are tallied by summing the encrypted vote ciphertext together. The result of the the result is this encrypted tally of the votes that corresponds to the plain text, the plain text, the equivalent plain text of summing all of the plain text votes. This is the real magic of homomorphic encryption. We can perform operations on ciphertexts that correspond to those same operations on the corresponding plaintext. And so it's quite literally just summing each of the encrypted votes together to produce this encrypted sum. That's our tally. We've then formatted it to a format that our decryption function can use, and jump down here to decrypt. So the tally is decrypted by each of the parties separately to produce a decryption share. The decryption shares are then aggregated together to produce the plaintext tally. And similarly, I think the aggregation process for the decryption, for the decryption shares, is essentially just summing them all together again. Although I'm not 100% on that part. I do need to dig back into it, into the decryption function here. And so note, as with the public key shares, aggregation of the decryption shares is simply summing them together. And because of that, it can be done asynchronously as well. You don't have to do this in any particular order. You can kind of collect all of those encryption shares once you become aware of them. Again, imagining that each of these parties are kind of nodes in a network, they can gossip those shares and add them together as they become aware of them. So with all of the decryption shares aggregated, we can, or created and then aggregated, we can then try to decode the result. And from that, we can print the result on screen and essentially make sure that it is what we expected it to be. Obviously, in a production environment, we don't have access to all of the plain text, so we can't do that kind of a sanity check. But in this environment, we can. And so, yeah, we can run this again just for the fun of it now that we have a better understanding of what's kind of happening under the hood. And so again, note here for 1,000 voters, it took us 1.3 seconds to encrypt all of the votes, and decryption time was less than a second, tallying time was a fraction of a second. And this essentially scales linearly with the number of votes or the number of parties. So if we were to bump this up to, say, 10,000 votes being cast and 10,000 parties, and then go and run that, then it'll take a little bit longer, but the times will be kind of rough multiples, roughly 10x what they were in the previous run. So yeah, that's the presentation, the workshop. I guess from here, happy to take it wherever you guys want. If we want to dive in and tear things apart a little bit more than we can. Otherwise, we can wrap it up and go check out the other talks. Oh, I guess since I forgot to put it into the notes anyway, this is me on Twitter. Nope, not capitalized. There we go. No worries. Thanks, everyone.
Great. All right. Any questions or requests or? Yes, hold on.
Hey, thanks. So yeah, I see your codes. It uses the FHE BFV or like the Rust crates, like the BFV scheme, right?
Yes.
Can it do all sorts of FHE operations? Can it, like, since it's based on polynomials, is it possible to do binary operations on the ciphertext?
So you can do addition and multiplication, and I guess from that you could, in theory, build out any kind of logic. But the noise growth obviously is quite large for every multiplication that you do.
Okay.
And so yeah, it's possible in theory, but kind of large computations require leveling, bootstrapping, and yeah, will get quite slow. So BFE is useful. It's a really cool scheme, but I think yeah, you need to be very deliberate about how you use operations to handle noise growth.
I see. Okay, understood. Cool. And does this Rust FHE crate has other schemes like CKKS or TFHE?
This one does not. So let's open up the crates. All right, so it's this crate only has BFE, but what it does have is this multi-party BFE crate kind of within it, which lets us do all of the threshold, or at least like the kind of multi-party version of this, and yeah, very kind of small, accessible crate to start playing with. I think we are importing. We're using a version of this that we forked, but the original one is by was it? His username reads like TLAU point, but he has a French name that I can't pronounce very well.
All right, I don't know.
Yeah. But I can dig up the or you can follow the links here to see where we forked it from.
Sure. Thanks.
Yeah, no worries.
So I guess following on from Amari's question then, so like if you were doing quadratic voting or something like that, then you wouldn't use BFE?
Yeah, well, not necessarily that you wouldn't, but if you were, if you're counting votes in a different way, then it would have radically different implications on noise growth, and so you would need to kind of manage that differently. It certainly wouldn't run as quickly as what this version does, and you would probably end up dealing with much larger ciphertexts or have some constraints over the number of voters or something like this. So it certainly could be done, but yeah, it would be quite a bit different. I think would be worthwhile exploring other schemes.
And then these are, I mean, I should probably just read this myself. These are finite fields, are they? The polynomials are over finite fields?
Right.
Not over, okay.
Right.
Cool.
All right. Anyone else? All right, let's thank Auryn again.
Thanks, everyone.